So this is going to be a quick video showing how to check a regression model's assumptions using residual plots. Now remember, these assumptions are the same as we saw for simple regression, we just have to extend our checking for multiple regression. So what are the assumptions and how do we check them? So we're going to remember that we're using, for this example, the model that uses age and weight to predict blood pressure. So our model is mu equals alpha plus beta 1 x1 plus beta 2 x2. Where x1 is age and x2 is weight. And we're predicting the true mean blood pressure for everyone of a given age and weight. So our first assumption is randomization. What this is really saying is that we have taken a random sample. The only way to check this is, how are the data collected? If we took a random sample, then we're good. If it's reasonable that the data or the sample is a reasonable or representation of the population of interest, then we can say that this has been roughly satisfied. So if it's reasonable that the sample is representative of the population, of interest, then we can check it. Now, we have to be able to justify that. We can't just say, yeah, we're good. We have to justify that with some rationalization. This, if we actually have taken a random sample using some random sampling device, then we're good. If we have not taken a legitimate random sample, if we have done some other sampling method that was not random sampling, but we can still make a reasonable justification, then we have to make that justification in our argument. The second condition is that the regression equation approximates the true relationship between the predictors and the mean of y. Really, we're hoping that the linear model that we're using is appropriate. And so before, in simple regression, we used a plot of residuals versus the predicted values. And so that would have been a plot of E versus the y hats. Well, we're going to do the same thing here. So on here, I've got my residual blood pressure, and I've got my predicted blood pressure. So I've got my residuals, my EI, so the residual for each observation, versus the predicted blood pressure for each observation. And what we want to make sure is that there are no patterns. So if we see something like a relationship or association, then that's a problem, because it means that there's another variable or another term that could be used to help explain that relationship. So it means that my model is not doing everything, and that there are other latent variables that have been left unmeasured that have been omitted from the model. So in this plot, I don't see any patterns or relationships. As my predicted responses increase, the residuals don't tend to increase, they don't tend to decrease, they don't curve or do anything like that. It just looks like a cloud of points. And so this looks good. Because there are no patterns, there's no apparent relationship between the residuals and the predicted response. So a bad plot for this would be something like residuals versus the predicteds. And if I saw something like my residuals tending to increase and then tending to decrease as my predicted response, in this case there would be a pattern. My residuals would be associated with my predicted response, and that's bad. We don't want anything like that. That's not the only way there might be an association, but that's one classic example of an association or a pattern that would indicate a problem with my model. In this case, my regression equation is approximating the true relationship. It doesn't look like anything's missing. My next condition is that my response, in this case blood pressure, has a normal distribution for each combination of the predictors. So this is saying that blood pressure is normal for every combination of age and weight. So if I'm talking about all people who weigh 90 kilograms and who are 40 years old, and then all people who are 90 kilograms and 41 years old, and then all people who are 91 kilograms and 40 years old. So any combination of age and weight, the blood pressure is going to have a normal distribution no matter what. To check that, the same way we did in simple regression, I do a histogram of the residuals. What I want to see is a unimodal and symmetric pattern, or symmetric shape. Or we can say a bell shape. Notice I'm not saying that it looks normal. Normal belongs in the population. My data are unimodal and symmetric or bell-shaped. In this case, if I draw a rough curve, it's unimodal, it's more or less symmetric. If there is a slight skew, that's okay. My F test and then the subsequent T tests are robust to those small departures. So my F test and T tests are robust to small departures from normality. Now I want to clarify, when I say the F test and the T test are robust, that doesn't mean that if I had a skewed distribution, robustness doesn't mean that the distribution is actually normal. It just means that if I have a non-normal distribution, if I have a skewed distribution, even though the F test and the T test really require normality, my results will still be valid as long as it's not too skewed. So if I had a histogram that looked like this, so approximately symmetric but with a slightly long right tail, the F test and the T tests for the overall model and the slope are still okay. This is not symmetric, but I can get away with it. If I had a distribution, however, that looked like this, which is clearly neither unimodal nor symmetric, this is bad. Because the F test can't handle this clear departure from normality. In this case, it's bimodal, and if I made it really bad, where I also had bimodal and asymmetric, or bimodal and right skewed, that skewness and that extra mode are going to cause real problems with the F test and those subsequent T tests. So, not unimodal. This is not symmetric. So this is not a small departure from normality. This is a big problem, and the F test and the T test are going to be bad. They won't work. Your results are going to be questionable. The next condition we have to check is that the response, in this case blood pressure, has the same standard deviation at each combination or at all values of the predictors. In simple regression, we just said that the response has the same standard deviation at all values of the one predictor. But now we have to consider at all possible combinations of, in this case, blood pressure and, of weight and age. To check that, I'm going to do what I did in simple regression, which is plot my residuals. So residuals versus my predictor. Only now I have two predictors, so I'm going to do my residuals versus each. So here I've got my residuals versus age and my residuals versus weight. But I'm looking for the same thing. So I want to make sure that when I draw an outline around my residuals, it doesn't tend to cone and it doesn't tend to fan out. So when I look at these two residual plots, I see basically the same width of the residuals. So how spread out are they? So here, from 0 out, it's about the same. And for weight, from 0 out is about the same, no matter where I'm predicting. So this is good, and this is good. A problem would occur if I had a plot and my residuals started off not too spread out and then got really spread out. So if here is 0, if my residuals were kind of small, but then got bigger, and then got bigger, and then got really big as my explanatory variable increased, we can see that I'm not drawing parallel lines, I'm actually drawing lines that fan out. So this fanning out is the problem. This is bad. A different way this could happen is if I were drawing my residuals and I saw something where for small values of my predictor I had a really big variability, but then it got smaller and smaller. This is also bad. We can see that I have this cone shape. Now, if I have a cone or a fan for any of my predictors, even if the others look good, like we have for weight or for age, if any of my predictors have this cone shape, then I have violated this condition. So if I have a bad plot here, but a good plot here, where everything is spread out the same amount, so if I had a bad plot, and then a good plot, this condition is not satisfied. So it has to be good on all plots, not just one. Because the condition is that y has the same standard deviation at all values of the predictors, not for all values of some predictors. All right? So we've talked about our standard deviation, we've talked about our normal distribution, we've talked about the regression equation and the appropriateness of the model and randomization. We know, of course, that we have to have a quantitative response and a quantitative explanatory variable, or quantitative explanatory variables. And finally, so let me throw that in as 4.5, we need a quantitative response and quantitative explanatory variables. And so this is just what kind of measures are we taking. And if we have categorical explanatory variables, we convert them to indicators. So finally, in practice, the sample size should be at least 10 times the number of explanatory variables. So if you have 3 explanatory variables, so if you have x1, x2, and x3, you need at least 30 observations. In our case, we have y hat equals a plus b1 times age plus b2 times weight. So that's 2 variables. We need at least 20 observations. And it turns out we've satisfied that because we have exactly 20 observations. So we are right on the border of being able to satisfactorily estimate these coefficients, to estimate these parameters. So how do we get these plots and jump? Well, I've already estimated the model. Here we've got my summary of fit, my R squared, 99% of the total variability blood pressure is explained by using age and weight. I have my analysis of variance, and I have my parameter estimates. We interpreted this in a previous video. What I want to do now, though, is I need to get my residuals, and I need to get my predicted values saved so that I can plot them. I need to be able to generate residuals versus predicted values, so I need to get my residuals and my y hats. And I need to get my residuals so I can do a histogram. And I already have my explanatory variables because I use those to generate the model. So to do that in JUMP, I go up to the red arrow menu for my fit model output, and I come down to save columns. I'm going to save my predicted values, so this will give me my y hats. And then I'm going to come to the red arrow menu again, and I'm going to save columns, and I'm going to save my residuals. Now you might see that nothing happened in my output, nothing expanded, I don't have anything new. It got saved in my data set. So if I come to my data set, I now see that I have predicted BP, so this is my y hats, my predicted values, and I have the residuals, so how wrong were my estimates of blood pressure. And now I can get whatever plots I need. So for example, if I want to do this plot, my residuals versus my predicted values, so residuals on the y-axis, predicteds versus on my x-axis, I would go to Analyze, Fit Y by X, and I would put my residuals in the y, and I would put predicted in x, and this is just how we've done scatter plots. So this is the same plot that's in the notes. I've got residuals versus predicteds, and I want to make sure that there is no association. Visually, I don't see one, so we've satisfied the assumption of no appropriateness of the model. To get a histogram of the residuals, I'm just going to request a histogram. So go to Analyze, Distribution. I want a histogram of the residuals, so histogram goes in the Y box, or excuse me, residuals goes in the Y box. I can request histograms only if I just want the plot. Otherwise, I can just hit OK, and I get a histogram of the residuals. I also get the descriptive statistics of the residuals if I don't request the histograms only option. So this is the same histogram that we saw in the notes. And we see that it's unimodal, roughly symmetric. With only 20 observations, it's hard to really describe a distribution. The next thing I want to do is I need the residuals versus each predictor. So I can request the scatter plot of the residuals versus age and the residuals versus weight. Now fortunately JMP makes this easy. I can go Analyze, Fit Y by X, residuals is my response, and then everything that I want to predict that against can go in the X box. So I want to predict or estimate or get a plot, of residuals versus age, and then I can get another plot at the same time of residuals versus weight. So this is not going to try to do a whole bunch of funky analyses. This is just going to say every variable that's in this X box, do a different plot for. So now I can see that I have residuals versus age in the first plot and residuals versus weight in the second plot. For the first plot on the left, there does not seem to be a cone or a fan pattern. So as age increases, the width of the residuals or the size of the residuals tends to stay the same. Similarly for the plot on the right, as weight increases, the size of the residuals or the spread of the residuals tends to stay about the same. So we've satisfied that condition. So this is a quick recap of how we check our conditions. They are the same conditions that we looked at for simple regression. The only extra work we had to do was creating a second plot in this case because we have a second explanatory variable. If we had 5 explanatory variables, all of this would be the same. We would just have to do 5 scatter plots here for residuals versus each of those 5 explanatory variables. I hope this helped.